Okay, so what last time we had discussed is, if you remember, direct product. And we have seen that internal direct product is isomorphic to external direct product. And we had seen example of plane for group G equals to plane for group EABC, where C equals to AB. And we had three subgroups, H1 equals to EA, H2 equals to EB, and H3 equals to EC. And what we have seen in the last and we have seen that G equals to H1 H2. This is direct product. It also can be written as H1 H3. It is also internal direct product or direct product now because they are isomorphic. Or that can also be written as H2 H3. So this is not unique. Yeah, the subgroups may not be unique, so they can be expressed in different forms. And what we had seen that so this is direct product. What we had seen that G is also equals to H1, H2, H3. If you take the product of all, then also that is equals to G, but this is not internal direct product. Right? Because every element did not have a unique expression in this. So they can be written in more than one way. So it is not internal direct product. This we have seen. And as another example, so this was example one, and another example I forgot to give as exercise, but I've already given for assignment. So show that find an abelian group. If G is abelian group, can be written as a direct product of its CELO subgroups. As a direct product of its CELO subgroups. So this is another very interesting, important exercise that you should try. All of you should try. So hint is that if order of G equals to n, so n we can write as, let us say p1 power, let us say alpha 1, p2 power alpha 2, and pn power alpha n. Right. So what is a p1 CELO subgroup? Highest prime order of p1. So we have to express G as G equals to P1, P2, and Pn, where Pi is the ith prime. Yes, Pi is the group, CELO subgroup generated by the ith prime. So it is the Pi CELO subgroup of G. It is Pi CELO subgroup of G. You can try with 2 primes, and then by induction you can extend it to this. Yes, but for this, what you need to, one exercise is needed. So why this is not internal direct product? We had seen, and we had seen one lemma also. This result. This was the lemma which we had seen last time. That if G equals to n1, n2, and n is internal direct product. If this is the case, then what is the relation between all these normal subgroups? That ni intersection nj. This is trivial. That means they are pairwise disjoint, and AB equals to, and the two elements commute, even if G is not abelian, but AB equals to BA for all A in Ni and B in Nj, whenever I is not equals to J. So here also I not equals to J. So this is we have seen, right? But what about the converse? Converse is not true. And we have considered above example for that case. Above example, G equals to H1, H2, H3, right? So G, and this is nothing but K, Klein for group. We have seen that this is not internal direct product, but you can see here the intersection of these two. That is disjoint. I'm not disjoint. I mean the intersection is trivial. H1 intersection H2. This is identity. H2 intersection H3. This is identity, and this one H1 and intersection H3. This is also identity. So mutually they are all disjoint. But if we multiply all this, all three, then we get EABC. So that is equals to, product is equals to G. But it is not internal direct product because every element did not have a unique expression in that. So the converse is not true. So when the converse is true, so that is a question. When is the converse true? So for that we have another exercise. This is also given in, I think, assignment I have given to this batch. The exercise is G is internal direct product of normal subgroups N1, N2, and N, if and only if, yeah, here now the converse is also true in this case, if and only if. So this is if and only if condition. The first thing is, by definition, we want G equals to, of course, the product of all this, N1, N2, and N. The second condition is that, yeah, internal direct product hoy. If it is internal direct product, then this is true. But if this condition is there, then it is not internal direct product. We need one more condition other than this. So no, not one more. We need different condition than this. So this says that Ni intersection, not Nj, but the product of all N1 up to Ni minus 1. Then Ni is here. So this is Ni plus 1 product up to Nn. This is trivial. This is trivial for all I. And then these direct products. Is it clear? So we don't need just Ni intersection Nj. This may be true, but we cannot say. As I said, the converse is not true. We have seen last time example, Klein for group. If you multiply all three of them, then this condition is satisfied. But G is not internal direct product because the expression was not unique. E we can write as E. E we also wrote as A, B, C. A, B equals to C, and C into C, that is C square, which is identity. So this was not there for Tron layer. The reason was because if I take what is H1, H2? H1, H2 is already G. H1, H2 is G, and if I take H3 intersection H1, H2, then this is what? This is H3 intersection H1, H2 is what? It is G. So this becomes G, and this is H3, which is not identity. That is the reason that Tron leta tha na, and we are taking 3. That was not happening. This is the reason. But if this condition is there, that ni intersection the product of all rest remaining all, not only just one, product of remaining all must be this. So must be trivial. So if that is the case, then we can say that G is internal direct product. Okay. So I hope this much is clear. Just recalling what we have seen, and then two exercises. Both are important exercises, which I gave in the assignment also. Yes. And so now let us go further. So next result is an important result, which all results, three results are there, two results, both are very important for us now. What we are going to see, our goal is, let me write what is our goal. For given order n, we want to determine, this is our target, we want to determine the number of different. At this stage I'm writing different, but actually different means different or distinct. That means what? When we say group means distinct, means that is non-isomorphic. Abelian groups. Yes, so for given any integer n, given any integer n, we want to determine the number of non-isomorphic abelian groups of order n. How many will be there? For example, n equals to 4. So how many groups are there? One we know, this is Z4, which is cyclic. Another one we know is plane 4 group, which is not cyclic. Yes, this is not cyclic, it is abelian. Yes, of course, abelian groups. I did mention, yes, abelian groups of order n. So this is abelian, plane 4 group, EABC. That is abelian, but not cyclic. Why it is not cyclic? Because there is no element of order 4. So it is not generated by single element. You see, if I try to generate it with A, so A square is identity, B square is also identity, C square is also identity. So it does not generate. A square, again, A cube is A raised to 4 is E. So you cannot generate by A, you cannot generate by B, you cannot generate by C. So that is a non-cyclic abelian group. And what about other groups? We have Z2 cross Z2. This is also a group of order 4. Oh, but Z2 cross Z2, as we discussed in the last class, these two are isomorphic. Yeah, it is same. So it is isomorphic to plane 4 group. Why? Because this is also 0, 0, 1, 0, 0, 1, and 1, 1. So this is also like EABC. This is E, this is A, B, and C. You can see identity 0, 0. A is order 2, 1, 0 plus 1, 0, that is 2, 0. 2, 0 is again in Z2, 2 means 0. So that is 0, 0. Similarly, 0, 1 has also order 2. 1, 1 has also. If we add A and B, we get C. AB equals to C. But here it is additive group. So A plus B equals to C. So you see that is isomorphic to plane 4. So there are only two groups. So it says that only two groups, two abelian groups of order 4. Only two abelian groups. Only two abelian groups. One is cyclic, which is Z4. Another one is, you can call it plane 4 or Z2 cross Z2. If you want to see as additive group, you can consider this. If you want to consider a multiplicative group, you can consider plane 4. But they are isomorphic. Yes, it is same. So This is our target. Suppose n equals to 5. Every group of prime order is cyclic. So Z5. Only one group if n equals to 5. What if n equals to 6? One we know is Z6. S3 is non-abelian. So S3 we are not considering. We are considering only abelian groups. Right? So one is Z6 we know. Is there any other group? This is cyclic. And every cyclic group of order n is isomorphic to Zn. So any cyclic group of order 6, it is isomorphic to Z6. So cyclic case to done. What about abelian which is not cyclic? Is it possible? Do we have Z2 cross Z3? Is it possible? So that is such questions are there. So how many total? And we don't want exactly always done or the list. Sometimes numbers are also useful. How many groups are there? Abelian groups. So that is our target for which there are 3 results. Today we'll do one result. Another result we have a last lecture. Last time Sanjay sir has taken my lecture on Thursday. So I was we are meeting after Wednesday again. So today I'm taking his lecture also, but then I shifted with Prajapati sir. So now I'm taking the first and the last one. So in the last lecture we'll do the second result, and for the third result we'll wait for the next class. Okay, so this is that result which I was saying. This says that every abelian group, and that is why direct product was important. Every abelian group, this is classification of the result. What I said, this is classification of all finite abelian groups. So whatever is given here, this is classification of finite abelian groups. Yeah, every abelian group can be written as every finite abelian group, of course. Can be written as a direct product of cyclic subgroups. Very important result. Direct product of cyclic groups, you can call it. Subgroups heterogeneous, it can be written as direct product of cyclic groups. So this is one of the most important result. Every finite abelian group, of course finite zero can be written as direct product of cyclic groups. Let us put it in some box. Yes, so this is one of the most important result in the theory of groups. Okay. Okay, let us prove this. See, by exercise 2 above. To do this exercise, that is why I said this exercise is important. Every finite abelian group can be written as direct product of its CELO subgroups. So if order of G is P1 power alpha 1, P2 power alpha 2, and so on, so then it can be written as P1, P2, Pn, where P1 is nothing but it is P1 CELO subgroup. So for example, if order of G equals to, let us say 24, so 8 into 3, so this is 2 cube into 3 power 1. So you can write this as P1 and P2, where P1 is 2 CELO subgroup and P2 is 3 CELO subgroup. So like this, one can write. So every finite abelian group can be written as direct product of CELO subgroups. So now it is sufficient to show that every CELO subgroup can be written as direct product of cyclic groups. We want to express G in terms of, so from exercise above, we know that. This you can also write the same in exam, because if this will be a longer, do not prove that exercise, otherwise the proof will be longer. So we know that every finite abelian group can be written as a direct product of question હોય તો પૂછજો any question if you have, if I'm going too fast આરામથી જાઉં છું. Direct product of its silo subgroups. What we have to show, every finite abelian group can be written as direct product of cyclic groups. So what is the first step? Sorry, the first step is to write G as product of its silo subgroups. So this has order some p1 power alpha 1. This is another group, it has order some prime power. This has order some pn power alpha n. Yes, so these are all capital P1, P2. So these are silo subgroups, and direct product it can be written. And now if we show that this can be written as direct product of cyclic groups, this can be written as direct product of cyclic groups, this can be written as direct product of cyclic groups, then we have G can be written as direct product of cyclic groups. Is it clear? So suppose this can be written as direct product of some cyclic groups, this can be written as direct product of some cyclic groups, this can be written as some direct product of cyclic groups, like this. If we can show, then this is G is nothing but direct product of cyclic groups. Right, so it is sufficient to show that every P silo subgroup can be written as direct product of cyclic groups. Then we are done. Take finite abelian group. First of all, express by this exercise, express that is direct product of, so it is product of P silo subgroups. And if we prove now that every group can be written, every P silo subgroup can be written as direct product of cyclic groups, then we are done. And G mathi go to the product of P silo subgroups, and from P silo subgroup we get a direct product of cyclic groups. I hope this is clear. So this is a statement what I have written above, that by this exercise what we know is every group, finite abelian group, can be written as direct product of silo subgroups. So it is sufficient. So it suffices to show that every abelian group of order p raised to n, where p is prime, can be written as direct product of cyclic group. All right, so it is sufficient to show that p power n વાળું હોય ને તો થઈ જાય, because write G as direct product of P silo subgroups, but this has order P1 power alpha 1, so it is prime power. And this can be written as direct product of cyclic group. Similarly, P2 can be written, it is a prime power, so it can be written as direct product. So combine this, then G can be written as direct product of cyclic groups. So it is just to show that for this it is sufficient. If any group of order P power n can be written as direct product of cyclic groups. So this theorem can be broken to this. So the result, again, I am writing the statement. Any group, any abelian, of course, G is given to be abelian, any abelian group of order P power n, this can be written as this also by above exercise. So now it reduces to showing this only. Because silo group in order kyo hai? Silo group has order P power, so it is sufficient to show this theorem. Any same statement I am writing, but arbitrary not leta. If order of G is n, then we know n can be written as P1 power alpha 1, but this is P1 silo subgroup, this is P2 power alpha 2, this is P2 silo subgroup. And for this individually, if we prove, then we are done. So any group, abelian group of order P power n can be written as direct product of cyclic groups. once again writing the same statement, cyclic groups. Okay, so now we prove this. So we can continue this proof. Okay, so now let G be a group. So I can assume let G be a group, and order of G equals to P power n, where P is prime and n belongs to n. Now this is the process. The first step is this is the first step. Choose A1 belongs to G of highest order of the maximal order, because it is finite. So order maximum, maximal order. Maximal I am writing because there may be more than one element of the same order. For example, plane for group. So what is the highest order of any element? Highest order E in order 1. Identity always has order 1. A has order 2, this has order 2, this has order 2. So highest is order 2. So which one to select? A, B, or C? You can select any one. Yes. So choose A1 in G, which has maximal order. Say P power n1. What is order of A1? Order of A1 divides order of G. But what is order of G? Order of G is P power n. So order of A1 is also some prime power. So let us say P power n. Okay. And then take the cyclic group generated by A1. So A1 equals to. So we have A1 is the cyclic group generated by A1. Then what is order of A1? Order of A1 equals to P power n1. Same order as that of its generator. They have the same order. Right. Now we select B2. So choose B2. The proof is constructive but not difficult. If you see, maybe you will have to see the proof more than once to get some idea. But the proof is not that difficult. If you still don't understand the proof, we may consider this by taking an example, maybe at the end once we finish the course. So choose B2 in G such that its image B2 bar in G quotient A1. Now take G quotient A1 and consider B2 such that its image B2 bar in G quotient A1 has the maximal order P power n2. Say P power n2. Right. So what is image means? What is the meaning of image here? Sorry. So this is a homomorphism. What is homomorphism? Someone's mic is on. Daniel, your mic was on. Yeah. Okay. So this is a homomorphism. G to G quotient A1. આ તો આપણે જોયું છે first unit માં. If n is a normal subgroup, then we have homomorphism G to G quotient n. કેવી રીતે મળશે? How do we get? So if I take any element B here, so B is mapped to PA1, X going to NX. આવું જોયું હતું ને, અને BA1 we call it B bar. This is the homomorphism. So it is homomorphism. First unit માં જોયું હતું normal subgroup હોય તો G going to G quotient n1. This is homomorphism. Right? So here B2 second element એવો choose કરવાનો so that its image. So once you have B2 here, what is the image of under this homomorphism? B2 in G quotient A1. This is B2 A1, which is B2 bar. Order of B2 bar is this. So that is that is order of B2 bar equals to order of B2 bar is P power N2. Yes. So what by image what we mean? What that is where B2 bar is? B2 bar is nothing but B2A1. It is a coset B2A1. Okay. So this has maximal order. Right. So this is there, and then we know that then we have, because this is homomorphism, order of image divides order of group. Order of phi g अपन જોયું છે ને order of phi g by this, by order of phi g divides order of g. By this we have order of B2 bar, that is the image. B2 bar is the image that divides order of B2. So the order of B2 bar divides order of B2, and this implies order of B2 bar is less than equals to order of B2, but that is less than equals to order of A1, because A1 has maximal order. So B2 also may be maximal or maybe less than that, right? So that is less than order of A1. And what is this? This is P power N2, and this is nothing but P power N1. And therefore what we have is N1 is greater than or equals to N2. Is it clear? From here, what is the first step? Highest order वाला element ले दो, A1, that has order P power N1, and take the first cyclic group. We want to express this G as product of cyclic groups, right? So first take the first cyclic group that is generated by A1. It has order P power N1. Now the second element must be chosen in this way, B2, so that its image. So હવે A1 વાળો પાછો element ના મળે એટલે what we do is we take the quotient, right? એક વખત મળી જાય એટલે પછી A1 કાઢી નાખવાનું. Therefore we are taking G quotient A1, so that B2 bar is in G quotient A1 and it has maximal order P power N2. Next one. So order of image divides order of the element. So order of B2 bar divides this. So therefore order of B2 bar is less than equals to order of B2. But A1 was maximal, so either they have the same order. So this is either less than that or equals to. So which is P power N1, and B2 bar has order P power N2. So we get N1 is greater than equals to N2. And now if we want to express G as product of cyclic groups, so if A1 intersection this B2 cyclic group generated by B2, this is identity, then we proceed further. Why we proceed further? By this exercise. That is why I said this exercise is also important, right? This is also important. It says that G is direct product if and only if you can write like this, and this condition holds. So once we have first normal subgroup A1, second A2 જોઈએ છે ને, so, and if we have two only, then A1 intersection A2 must be identity. So if that is the case, then call this as A2. Yes, call this as A2, and we can proceed further to find A3. But this may not be the case. So if, however, this may not be the case. That is, we may have A1 intersection B2 is not identity. So there is an element common. So that means there is an element here which is also in this. Is it clear? બંનેમાં element common છે. So cyclic group generated by B2, આના elements કેવા હોય? What does this group look like? E, B2, B2 square, B2 cube, B2 power 4, and so on. ક્યાંક તો પૂરું થતું હશે. So there is some element of power B2 which looks like power B2, which is in A1. So by our construction, note that B2 power P power N2 is the first element. This is the first element which belongs to A1, which is the first power of B2. This is the first power of B2, which belongs to A1 by our constructions. So I ask you to verify this. In the notes also I have written verified. And what does this mean? I'll give you a hint. So what we have to show, P2 power K does not belong to A1 for K less than P power N2, right? And if conversely you try to assume this, suppose this belongs to this A1, then what happens to B2 bar power K? Check this. So this is just verification. I leave it to you. In exam, you need not write this. But this is the first power. Of course, intersection is non-empty. Intersection is non-trivial. That means there is an element which is in this cyclic group, which is also in A1. So in this cyclic group, elements are of the form B2 powers of B2. So there is some power of B2 which falls here. And what this says, that this is the first power, P power N2, is the first power of B2 which is in A1. So therefore, why it is the first power? So that is the part to verify. So this is to verify. Right. So therefore, B2 power P power N2 belongs to A1. But what is A1? A1 is nothing but the cyclic group generated by A1. So this implies that B2 power P power N2 equals to A1 power I, because elements here are of the form A1, powers of A1. So that means this is some power of A1 also. So it is power of B2 and it is some power of A1 also for some I. For some I. Right? Then let us take both sides power P power N1 minus N2. So then B2 power P power N2, P power N1 minus N2 equals to A power I and P power N1 minus N2. But then this implies, N2 N2 gets cancelled, P power N2 N2, right? N2, so this is nothing but, let us write like this, A power I, this on the left hand side, N1 minus N2 equals to P2 power P power N2 plus N1 minus N2. So this gets cancelled. So this is B2 power P power N1. And this is identity because N1 is greater than N2. Right? Again, for something for you to check, this is identity. I have written the reason. Because already B2 power P power N2, the order is less than equals to order of A1. So if, and so suppose B cube identity thatu hai, B raised to 2 raised to 3 is identity, B raised to 8 is identity, suppose B raised to 2 raised to 3, so that is identity. So if I take anything less than 3, right, if I suppose this is the case, okay, that means suppose this is identity 2 square, so suppose B power 4 is identity. So if I take anything greater than 2, so what will happen if I take B power this? So this is nothing but it is B power 8. What is B power 8? So I can write that as 2 square and power 2, 2 raised to 1. Right. So this is itself identity, and therefore this larger. If I take larger power, prime power, then of course that is identity. Right? So just check it. Right? So this one to check. I'm removing this. You can check. So it is N1, N2 already is identity. Let me put a question mark here so that you can verify. Okay, so now what happened here? Uh, A1. So this is A1. A1. A1, no, this power has given us identity. So and what was order of A1? Order of A1 was P power N1, highest, maximum, right? So order of A1 was P power N1. So order divides this power. So we know that if order of A is N, and if A power M is identity, A power M is identity, then what is the relation? That N divides M. Order divides this power, whichever gives identity. So what we have relation here also we have therefore, since order of A1 is P power N1, we have, or we can say that P power N1 divides I times P power N1 minus N2. But then this implies P power N1, P power N2 multiplied by P power N2. So that divides P power N1 minus N2 cancel there. Now cancel out P power N1 because it is non-zero. Right? So P power N2 divides I. And so this implies I equals to some J times P power N2 for some J. Right? And if that is the case, then now put the value of I here. So put the value of I in let us call it star. So putting the value of I in star, what we have, B2 power P power N2 equals to A1 power I, so which is nothing but A1 power J and P power N2. So multiply by inverse. So this implies A1 power minus J P power N2 and B2 P power N2 equals to this identity. So right hand side I brought this side. So I brought this side. So that gives us identity on right hand side. But then this is the common power P power N2. So this is A1 power minus J B2 and whole raised to, because it's abelian group, so xy power n we can write as x power n y power n. So this whole power, this is identity, and now we call this element as A2, right? So take A2 equals to A1 power minus J B2. Then what we have? Then A2 power P power N2 is identity. See, we have got another element whose P power N2 is identity, and we claim that A2 is our required element. A2 is the required element. Why A2 is the required element? So let us claim that A1 intersection cyclic group generated by A2 equals to identity. Okay, yeah, so I know I have time is over, but I would like to finish this in maybe 5 minutes. Now this is over. So the process, you see, we started with the first group, maximal order. Okay. Second element, A1 should not bother us. So we take G quotient A1. Therefore, second maximal we take such that It is in G quotient A1, so second power P power N2. Now, if you want to express as direct product, we need this condition, that intersection of one with product of all others. So here A1 was cyclic group. So it should be intersection with product. So here if there are only two, so this intersection with this must be identity, then we can proceed to find A3. If this is identity, then we are done. If it is not identity, then we need to find some other element whose order is P power N2. Instead of B2 power P power N2, we need to find something else, some other A2, such that A1 intersection cyclic group generated by A2 is identity. And that A2 has arrived. A2 has arrived. So this is the claim. So suppose this is not identity. This is what we want to. So let A2 power T belongs to A1 intersection A2. Of course, A2 power T આમાં તો આવે ને. So therefore, we say that this. What is the meaning of this? For some T. How do we show that this is identity? કેવી રીતે બતાવી identity? We show that this is identity. Some element here belongs this. So common element. So element here is of the form A2 power T because the cyclic group generated by A2. So let us say A2 power T belongs to A1. What happens? So A2 power T belongs to A1. What is A2? Okay, A2 we know here. So A2 we know. So this implies A1 raised to minus J B2 power T belongs to A1. Since A2 equals to A1 power minus J B2. But because it is abelian, so શું થશે? This is minus A1 power minus JT and B2 power T belongs to A1. So this implies B2 power minus B2 power T belongs to A1. Why? Because આ તો already છે. This element, this part is already inside A1. This is an element of A1. Right? Since because A1 already belongs to A1. In fact, we have this. A1 is cyclic group generated by A1. So A1 આવે છે, so this implies A1 power, whatever powers of A1 minus JT, that is in A1. So if we multiply by this, so if A belongs to H, so AH equals to H. So multiply by this both sides. So here it is already in A1. So it is, I can write this as A1 only. Right? I don't need to write here આની બદલે આવું પણ લખી શકાય here A1 power JT બંને સાઈડ મલ્ટીપ્લાય કરી A1, but this is A1 because this already belongs to this. Okay, so B2 power this belongs to the, what is the coset? B2 power T A1 is A1. Is AH equals to H if and only if A belongs to H. This we know. So B2 power T belongs to A1. That implies this coset is. But then what is this coset? This means this is B2 A1 power T equals to A1. Equals to A1, which is nothing but EA1. Right? See, what is NA, NB? It is NAB. So if what is NA, NA? No. So that is NA square. Right? So what is B2 power? So this is B2T, B2 A1, B2 A1, B2 A1 T times. So B2 A1 power T. That's the definition of coset. But what is B2 A1? B2 A1 was the image here. B2 A1 was B2 bar. And B2 bar has order P power N2. So B2 bar is identity. So B2 bar power T, this is equals to A1, which is EA1. So B2 bar is identity. And because of this, what we can say that therefore order of B2 bar divides T, because this is identity in G quotient A1. So B2 no power b2 bar power t is identity. Therefore, order of b2 bar divides t. This implies p power n2 divides t. Or this implies that t can be written as some s times p power n2. So finally, we started here. A2 power t is in A1. So therefore, A2 power t, what will be A2 power t? Therefore, A2 power t equals to A2 power s power t and 2, because t is this, but this is A2 power p power n2 and power s. A2 power p power n2 is identity. એવી જ રીતે લીધું હતું. This was how A2 we selected. This is how A2 was selected. So that is identity. This is e power s, which is e. And so see, p power n2 divides t, and any power of A2 power t identity, then that is divisible by p power n2. So that is order of A2. Therefore, order of A2 equals to p power n2, and A1 intersection cyclic group generated by this is identity. So take A2 equals to cyclic group generated by A2. Okay. So we have A1, then we get 2. A1 intersection A2 is identity. Now we continue this process. So last 2 lines. So now choose B3 in G. However, B3 કેવો લેવાનો such that its image will be, now let us call it B3 bar in G quotient. હવે product લેવાનું હોય A1 A2 has maximal order say p power n3. So then we get n3 is greater than equals to, so n1 is greater than equals to n2 is greater than equals to n3, and A3 intersection A1 A2, A2 intersection A1, so A3. So if B3 works, then fine. If B3 doesn't work, if A1 A2 intersection cyclic group generated by B3, this is identity, then proceed further. And if it is not identity, find A3 and take capital A3 equals to cyclic group generated by A3, as we have done earlier. So then we have A3 intersection A1 A2 is identity. And continuing this way, we get G equals to A1 cross. We can write cross also. Product ગમે એવી રીતે લખી શકીએ AK, where AI is a cyclic group generated by AI of order p power ni, where n1 is greater than equals to n2 is greater than equals to, and so on, is greater than equals to nk is greater than 0. Okay. So this completes the proof, and you can watch the video. If you have any difficulty, I can repeat it again, but this is a constructive proof. Okay. And then we meet again in the last lecture.